This is the outline of Lab 1 report. It has 5 main sections as shown. Each section contains several subsections, each consists one or more tasks. A task can be a question, a calculation, or assignment to build circuits, or do measurements and demonstrations of the circuits. To complete a lab assignment, do every task in the lab report outline. There is one-to-one matching between the list of tasks and the lab guide app items. After clicked open, the app will announce the follow. Welcome to Lab 1. Please allow up to 30 seconds or so for the pages to load when switching. A click on the drop-down menu shows 5 sections. They are organized into 3 apps. The first app is for Introduction and Part A. The second is for Part B. The third is for Part C and D. Run only one app at a time. That is, after one app, close Mathematica or quit local kernel before open another app, especially for computer with limited memory. For the first app as an example, it will also announce. This is Part Introduction and Part A. Please use the forward and backward button, or the drop-down menu to move between the pages. If Mathematica crashes or is not responsive when switching between the sections or steps within a section, close Mathematica and restart the app. Lab 1, Part Introduction has 6 items. This is Item 1, which includes a question and the instruction to assemble your breadboard, labeled with your name and student ID. Take a photograph of the assembled breadboard, and insert the figure in your report. To use the breadboard, one must have a way to supply electrical power to it. This is done via the binding posts. The 3 binding posts are usually for plus voltage, minus voltage, and the ground, which come from an external power supply. One should mount and secure the binding posts on the unassembled breadboard. There are a few videos below with more details. Click forward for next step. The next 3 tasks are about the breadboard and how to use it. Use the corresponding lab guide app for hints of the questions. The breadboard has holes with internal electrical connections which allow inserted elements to have electrical contacts, also known as ohmic contacts. This eliminates the need for direct wiring from one device terminal to another's. Click the applet below for a representative illustration of the electrical connections between rows and columns on a breadboard. For additional illustration and more details, watch the YouTube video or similar about the built-in electrical connections inside a breadboard. The applet is not a realistic mechanical drawing, but only an illustration of the electrical connectivity of the various rows and columns on a breadboard. Hold your breadboard in your hands. Use the app controls to move the breadboard illustration just like what you do with the physical breadboard in your hands. The graphics of the breadboard backside intentionally exposes the lines showing the electrical connectivity of the red and blue power rails, and the many 5-hole rows. Of course, the physical breadboard backside doesn't have such exposure. While looking at the breadboard in your hands, envision in your mind what the electrical connections inside the breadboard would look like, if the cover could be made transparent. Move, tilt, rotate the real breadboard in your hands, and use the applet for illustration. It takes only a short time for you to start getting an image in the mind, or a gut feeling, how the breadboard works, and how to use its built-in electrical connectivity. Hence, one can use a breadboard without an excessive use of wires to connect the electrical devices. Of course, wires are still needed, but only with a moderate number. How to supply power to the breadboard. It is very dangerous if we connect AC power to the breadboard binding posts. A person can get electrical shocked, and a shorted circuit can cause fire. In this lab, we only use the low voltage outputs from a DC power supply. See the figure below for a typical example. It is strongly recommended to assemble the binding posts according to the color scheme as shown. The reason will be clear in Lab 4 on op-amp. Below is a common power supply in the undergraduate lab. It allows one to control the voltage and limit the current. At home, you can also use fixed power sources such as batteries, adapters, and other popular electronics DC power sources. This is the end of introduction. Slide to close this step and go to the top to move on to Part A. Again, please be patient and wait for the pages of Part A to load. This is about the necessity of electrical currents. Electrons must move to carry power and energy to do work around a circuit. Whether it is for mechanical power like a motor, or logic operations like changing the state of transistor gates in a computer chip. Hence, without an electron movement, which is an electrical current, a device will not be functioning. This Lab 1 is about electrical current. This app helps review its basic concept. It is based on the classical, also known as the Drude model of charged carrier transport. It is not accurate with respect to the carrier quantum behavior, but is good enough for the electrical current concept in this course. Can we see a current flow? It all depends on the definition of C. The pictures below show that we can see indirect evidence of current flows. The left figure shows the evidence through current-generated heat, which results in thermal or infrared radiation. The right figure is the evidence of current flows via the radiation of atmospheric atoms and molecules excited by the current. The only way to know precisely and accurately how much a current is to measure it. We will learn how to measure a current in this lab. There are a few useful videos as shown about using common instruments to measure a current. LED, used in the light bulb that is replacing the old incandescent bulb, is a simple device that emits light in proportional to the current. Interestingly, the LED light emitting mechanism is not that far from the atmospheric lightning shown earlier. As an electron passes through a LED, it drops its energy by emitting light, just like the excited electrons in atmospheric gas ions, atoms, and molecules drop their energy and emit light. The higher the current is, the brighter is the LED. Hence, we will use LED throughout the course as a visual current indicator. It roughly indicates the magnitude of the current in the circuit segment containing it. This can help better intuitive understanding of a circuit with direct visual cues. This is the end of Part A. Please go to the app for Part B. Part B has 5 sub-items that include both questions and instructions to build circuits and do measurements. Hence, we need to discuss about the hardware for the course. The figure on the side shows a typical electronic hobby kit. Most tools are not required. However, it is convenient to have handy tools such as needle nose pliers, wire cutters, small screwdrivers, and tweezers. These are useful not only for this course, but also as general-purpose household tools. Hence it is recommended to have them available. For voltage sources, both at home and in the lab, you can use the DG Lent AD2. It can give a maximum of +5 and -5 volt for 10 volt differential. It is sufficient for many experiments, but not all. In the lab, one can use the BK Precision. Watch the YouTube video how to use the instrument, or ask the teaching assistant or lab supervisor for additional help. It is recommended to consider acquiring additional power supplies for home use. For example, AC/DC adapters that can be recycled from electronic equipment such as camera, or LED strip lighting power sources. They are relatively inexpensive and more cost-effective than batteries for long-term uses. The reason is that in Lab 4, if done at home, will require power sources as shown. Hence, although this is Lab 1, one may as well acquire these types of power supplies to be used right now, as they will be needed later on anyway. If the lab has these as spares, you can check them out as loaners. For voltage measurements, the DG Lent AD2 is sufficient to use with its 2 scope channels as labeled in the picture. However, if there is a need for more accuracy and higher precision, such as Lab 3, the Agilent multimeter in the lab is a more suitable instrument. Follow the YouTube video on how to use it, or ask the teaching assistant or lab supervisor for additional help. For current measurements, at home, you can use a household digital multimeter or equivalent as shown. At least 3-digit precision is recommended on the 200 mA scale or lower. There are many higher performance similar instruments that are modestly more expensive. In the lab, especially when high accuracy and precision are important, such as Lab 3, the Agilent multimeter is a more suitable instrument. Follow the YouTube video on how to use it, or ask the teaching assistant or lab supervisor for additional help. If the lab has spare handheld multimeters, you can check one out as a loaner. For the first-time user of the DG Lent AD2, it will take some time to get used to it. For Lab 1, you can download a few DG Lent files as shown that have preset configurations for certain measurements and demonstrations. It is desirable to learn how to use the AD2 and set up the configurations oneself to do lab work. These files are just examples so that one can get started and get a hang of it. Ask the teaching assistant or lab supervisor for any additional help. There are many resistors in your kit. Some will be used in Lab 1. For a first-time user, use a reference color code chart to read your resistor nominal values. Then, use any digital multimeter shown previously to measure the actual resistance and verify. Throughout this course, it is necessary to measure and report the actual value of any resistor used in a circuit. If you don't have or lose certain resistors needed, you can obtain replacements in the lab. A number of LEDs will be distributed. However, the supply might be limited. And based on past results, first-time users may have many of them damaged, as LEDs are somewhat sensitive. They are not available for replacement in the lab. Hence, you can obtain LEDs on your own, and they are quite inexpensive. A package of 500 LEDs can last for years, beyond what used in this course. These pictures show the LEDs used in Lab 1. There are certain minimum numbers of LEDs for Lab 1 circuits. But one can use as many as available, and up to the capability of the power supplies. There is at least one potentiometer in your electronic kit. It is just a resistor, whose resistance can be varied by turning the knob. An optional circuit for Lab 1 as shown, uses a potentiometer to demonstrate how the current can be controlled, which can be seen via the variation of the LED brightness. The first circuit of this Lab 1 is a simple resistor circuit with the schematic as shown on the left. Which wiring configurations on the breadboard on the right are its correct implementations. Draw the lines over the rows. Only a complete path starting from the power source terminal on the red power rail, to the sink terminal on the blue power rail, is a valid closed circuit. The wiring configurations highlighted by the blue arrow paths are the correct circuits. If you feel unfamiliar with the previous explanation, try this applet exercise. If both terminals of a passive device are connected together by a conductor, no current will pass through it because electrons will flow through the path of least resistance, which is the conductor. Hence, the device cannot be active. Can you visualize to determine which resistor on this breadboard cannot be used? The two terminals of the red resistor are connected, or shorted together. It means the current will prefer to flow through the conductor underneath, not the resistor. Hence it cannot be used. The blue and green resistors are in a correct configuration for usage. For a breadboard user beginner, a mental exercise is to visualize a current path flow in the mind. If a flow does not form a closed circuit, then it is not valid. A few such mental exercises will enable one master breadboard wiring quickly. Next task is to practice current and/or voltage measurements on the single resistor circuit you built. There is a standalone app shown here that is relevant to the rest of this lab. Do not get confused between this standalone app for circuit analysis versus the lab guide apps. Instruction and usage of this standalone app is given in another presentation, and whenever convenient, take a digression momentarily to learn the app in preparation for the rest of the lab work. The following shows a recommended practice how to measure voltage and/or current in situ on a breadboard. Insert 2 wires or pointed probe tips into the holes for which voltage or current is to be measured. Do not touch or clip the probes onto the legs of the devices in order not to disturb the circuit. Then, attach the 2-meter probes, either hook or alligator clips, onto the upper ends of the inserted wires. Apply the suggested technique above to measure the current and voltage of the single resistor circuit. You are encouraged to tinker and explore how to do it, as long as you obtain the correct results. This is just one suggested approach that involves the use of an extra piece of wire, called jumper wire. Observe the 2 alternate views back and forth, showing how the jumper wire can be put on and taken off for current measurement. The amp meter we have is not of the magnetic inductive type and a circuit path must be broken open to insert the probe. For voltage measurement, the probes can be left alone as shown. There are 2 options for current measurement instruments. If you are at home, use the home-based multimeter. One probe should be plugged in the port label with milliamp, whether 200, 300, or whichever on your meter. Do not use the port labeled with unit in amp. The other probe should be plugged in the port labeled COM. In the lab, use the Agilent multimeter with the same considerations of port labels. For voltage measurement, there are 2 options like the current measurement also. But one probe should be plugged in the port labeled V. There is a third option if you are familiar with the AD2. This option is very desirable and convenient, and if interested, watch the part B5 later of this presentation. One more note worthwhile to mention, is that although it may make sense to put in 4 wire probes on the breadboard, 2 for the current and 2 for the voltage, statistically, it is not desirable. The reason is that the risk of clipping the instrument probes on the wrong wires is quite high, and if the current measurement probes are clipped on the voltage probe wires, the fuse can be blown out, and such incidents were often reported by the users. Hence, it is not recommended to have both wire probes for current and voltage on the breadboard at the same time. The current must flow through the amp meter as illustrated for a measurement. Polarity of the probes is relevant to the reading of the current, whether positive or negative. If the source voltage connected to red power rail is positive relative to that of the blue power rail, the current should be positive as shown, provided the probes are plugged in the amp meter with the appropriate polarity. Swapping the amp meter, or voltmeter probe clips attached to the inserted sensing wires will give an opposite sign current or voltage value. Try that to gain familiarity with instrument polarity. The objective of this step is to gain familiarity with LEDs, as they will be used throughout the rest of the course. If you are already experienced with them, just perform minimal tasks that show you can build a single LED circuit and observe the emission brightness change versus current. It is strongly recommended you have the DG Lent AD2 ready, and not use batteries at home as power sources. In the lab, you can use either the AD2 or the lab power supply. Contact the teaching assistant if you do not have access to proper instruments. Here, we will use LED, which will light up when a current passes through. Throughout this course, LED is used as a visual current indicator. It is not a substitute for accurate current measurement, but most of the time, its brightness is sufficient to give us a gut check that the current is in the right designed ballpark. If it suddenly flashes too bright, or goes dark, This indicates something amiss. Polarity of voltage and current, as discussed previously, is important for LED. It has two terminals. One is called anode, which usually has a long leg and should be connected to a voltage that is higher than that of the other terminal, called cathode, with a shorter leg. Here the voltage must be positive, which means the plus terminal of the power source must have a higher voltage potential relative to the minus terminal. For the first-time LED user, this is a helpful mental exercise. Which of the 5 LED breadboard wiring configurations as shown will work, that is, emit light? In fact, if all 5 are wired as shown, none of the LED will light up, and the power supply will indicate it is short-circuited. Do not do this with batteries at home, because batteries do not have built-in short sensor to break the circuit. By removing just one wire, you will see that the power supply will no longer be shorted, and some LEDs will emit light. After the above mental exercise, by visualizing in the mind the current flow, you can choose a LED wiring configuration that works, one with a light blue arrow as shown, for measurements. Follow the same suggestions as in the single resistor circuit above, such as using a jumper wire to open the circuit and insert the current measurement probes. For the first-time breadboard and LED user, if the previous mental exercise on LED wiring configurations is not obvious, this additional applet can give a 3D perspective of a correctly wired LED that lights up, versus an incorrectly positioned LED that will not light up. The dark LED is inactive because the current bypasses underneath its terminals, rather than going through the device. Also for the first-time breadboard LED user, this applet allows one to simulate putting an LED on a breadboard for practice. Click on the LED icon, a LED appears at a random position. Use the Z control to push it down and fix it in place. Use the XY cursor to select a position for one end of wire A. Select a position for the other end, and wire A appears. Push wire A down onto the breadboard. Do the same for wire B. First select a position for one end. Then, select a position for the other end. Wire B appears. Push wire B down onto the breadboard. Click the power button, the LED will light up if wired correctly. Otherwise, it will remain dark. Lastly, there is the option to click a 3D animation of the current flow to reinforce one's understanding. In summary, for the first-time breadboard and LED user, a combination of simulation with a few circuit building trials and errors can help one quickly get a hang of it, and be able to use LEDs with ease for the rest of the course. When using the DG Lent AD2 to drive an LED, move the voltage control slider very slowly from 1.8 volt to higher. This app has a fine voltage control that can simulate a feel for the rapid rise of a LED current from 0 to potentially damaging level above a voltage value known as the contact potential, or sometimes, might be referred to as the band gap potential energy. As shown on the right chart, although some LED are capable of high current and high power, most and those distributed to you in this course should be used under 25 mA or 50 mW. Hence, when sliding the AD2 voltage supply control, monitor the amp meter to ensure a safe current value, such as under 10 mA, or at least use the eye to see that the LED does not light up too fast and too bright. Do not be concerned if a few LEDs are damaged. They are inexpensive and the teaching assistant can provide replacements if available. If you are at home, only have batteries or similar DC voltage source, and not the AD2, you can get credit for both step B3 and B4 by building a circuit using the potentiometer in the kit. As shown in the circuit on the right, the potentiometer is put in series with resistor R1, which you can choose to be between 100 ohm and 1 kilo ohm, which is in the picture. This value depends on your voltage source, such as 3, 5, 9, or 12 volt. The circuit in the photograph was designed for a voltage up at 12 volt from a DC adapter, and the 1 kilo ohm resistor limits the current to around 10 mA. Start by turning the knob all the way such that you have 10 kilo ohm between the two terminals used. Note that the third terminal is not connected to anything. Without the AD2, it is likely you have only one digital multimeter at home. You will need to measure the voltage between node A and node B, so that you can use Ohm's law to infer the current through the LED to keep it at a safe level. Then, you will also need to measure the LED voltage between node B and node C. Hence you should leave one probe at node B, and move the other probe back and forth between node A and C. It is recommended that you leave 3 probing wires in place for the 3 nodes on the breadboard, avoid pushing or pulling them in and out. Just clip and unclip the multimeter probes on the upper ends of the probe wires. Tune the potentiometer the other way slowly while monitoring the voltage across R1. You should see the LED getting brighter. Use Ohm's law for the LED current, and for each value of current you write down, measure and record the corresponding voltage across the LED. Remember about the polarity and change the sign as needed. Tabulate and graph your data at least 4 points in your lab report. Step B4 involves building a circuit with both a resistor and a LED in series. Then perform current and voltage measurements like previously. Which ones of these 4 wiring will work, that is the LED will light up? Like previously, one can do a mental exercise, imagine lines drawing through all the relevant connected holes on the breadboard. Then, any circuit that has all the lines connected continuously will allow a current. As shown, there are 3 that allow current flow, as indicated with the highlighted arrows. But one is not what intended, because the LED will not light up as both of its terminals are shorted. This is the same situation that was discussed in B3 above about LED that will not light up. Thus, we can select one of the 2 that are valid, and build a circuit. Consider this wiring configuration. Measuring the voltage is similar to what done in B2. There are 3 options: at home, in the lab, and using the AD2 either at home or in the lab. If you wish to use the AD2, follow the instructions in B5 of this presentation. To measure the current, again, one has to break open the circuit. Here, we don't use a jumper wire, but break open directly one power supply wire. Then perform a current measurement like previously. One can alternatively use the other power supply wire. If the circuit works, but the LED goes dark when doing measurement of the current, envision if the current flows through the amp meter with correct ports. If the current flow path is correct, but no current reading, try to switch the current probe from milliamp port to amp port. If there is still no current flow, one high probability reason is a problem with the fuse. In step B3 and B4 previously, it is clear that using or designing a circuit with LEDs requires data of current and voltage behavior, known as the IV curve. As shown below, the IV curves are different for different types of LED. However, it is not reliable to use previously calibrated data such as those shown in the charts for other LEDs not from the same batches. Even the color of a LED cannot be relied on to use as a reference. The reason is that many LED colors are secondary emission from luminescent materials that are excited by a gallium nitride blue LED. Thus, 2 nominally green LEDs for examples, may have totally different IV characteristics. Many new colors such as pink, amber, yellowish white, or white for examples, are similar to the blue LED. Hence, it is best to calibrate the specific LEDs that one has at hands, and to be used in a circuit. Fortunately, with the AD2, it is actually quite easy to obtain an IV calibration. Step 1. Build a simple RLED circuit as shown on the breadboard. It is just slightly different, but you can still refer to step B4 above. Use a nominally 100 or 200 ohm resistor, and measure its actual resistance, preferably with 4-digit precision. If your multimeter at home has only 3 digits, it is fine. The LED is whichever you choose to calibrate. Step 2. Use a 6-pin connector that comes with the AD2 kit. If you don't have it, just use 6 short pieces of wires, each with one end inserted onto the breadboard, the other end sticking up like the connector. There are two short jumper wire connections. Step 3. Locate the various cables from the AD2 connector that comes with the kit. There are 3 pairs of cables, signal 1, scope 1, and scope 2. Each pair has a plus and minus. Insert the cable ends onto the 6-pin connector gently, avoid bending or breaking the pins. There are some flexibility that you can interchange the cables if necessary. 1. Signal 2 can be used instead of signal 1. Then, the waveform programmed on the DG-Lent software control should be configured to output to signal 2. 2. The scopes 1 and 2 can switch places. 3. Even the plus and minus of each scope can be swapped, but the sign must be corrected after the data acquisition file is saved. 4. Do not swap the signal plus and minus, unless the sawtooth waveform programmed on the DG-Lent software control is changed of its polarity. There are a few approaches to vary the voltage to do a voltage versus current measurement, for any circuit, not just LED of course. The first is manual, like turning the knob of a power supply. Set a voltage, then write down measurements of the actual voltage and current. This is laborious and slow. The second is to use a computer-controlled instrument such as the AD2. Instead of a mechanical knob, one can use the mouse to control a slider to set a voltage. The third and most convenient is to program the computer to do all automatically. The AD2 can be set to change the voltage up and down automatically, no need for manual mouse control, while also recording the voltages. This can be done at very high speed, for example, 1000, 10,000, 100,000 times or more per second. Obviously, this is why we will use this approach not only in this case, but also for many other measurements throughout the course. As an extra note, the varying voltage is also called a signal or a waveform. It is just another word for any kind of time-varying voltages. After setting up the waveform, click Run and the AD2 signal 1 is sent to the circuit on the breadboard. Click the scope function, and the AD2 automatically and simultaneously measures, records the voltages across the resistor, which is scope 1, and the LED voltage, which is scope 2. Per Ohm's law, the resistance voltage is proportional to the LED current, and hence, the IV curve can be displayed by selecting the XY function of the AD2 scope control, as shown here. Adjust the waveform amplitude as needed to have the current up to 20 or 25 mA. Just click Save, select .csv format, and enter a file name. The measurement is completed. The saved data is input into a numerical model fit computer code to yield the LED model parameters. The model fit code written with Mathematica is available for download. With the LED model parameters, simple codes such as shown here can return IV or VI values for any circuit calculation. Throughout this course, if you wish, you can import your own LED calibrations into the various apps that calculate the circuits with LEDs. By default, the apps use calibrations of the LEDs that are distributed to you. Often, even if you don't calibrate the LEDs purchased on your own, the results are close enough for all practical intents and purposes in this course. As examples, these are calibrations for a batch of old 5mm LEDs. The newer 3mm high-efficiency LEDs are similar, and many are essentially blue LEDs.